How do two observers observe the same event? How does time change? How does space change? That's what we will study today. So let's imagine two observers. Both of them will observe the same event. So let's call them Alice and Bob. Alice is standing at a platform while Bob is inside a moving train, and it's moving with velocity v. So let's say that at some point and some time, an event happens. Let's say a flash of lightning. Now, Alice is at the origin, her origin, O. And so her description of the event depends on coordinates x and t relative to the origin O and relative to her time frame. And so the event occurs at a distance x from her and at a time t. On the other hand, Bob measures the same event from the origin O prime, and for him it occurs at a distance x prime and at a time t prime. So we have one event but two coordinate systems. The question now becomes, how do we convert between coordinate systems? How do we go from xt to x prime t prime, Bob's coordinates, from Alice's to Bob's coordinates? So let's tackle what sorts of relationships there can be between these coordinates. So x prime, let's say, is some function of x and t, f, and t prime likewise is a function g of x and t. What sorts of functions could f and g be? Could, for example, x prime be of this form, contain a quadratic in terms of x? The answer is no, for the very simple reason that 1 meter in one location, say London, has to be the same as 1 meter in any other location, say Paris. And so the only feasible relationship or transformation from xt to x prime must be linear. So both x prime and t prime are linear functions of x and t. They take this form with some unknown coefficients a, b, c, and d. And so our task now becomes, how do we find these coefficients? Well, we're going to use some simple principles in order to do this. So let's start with the first principle. Bob's origin is moving with a speed v. He's on the train. So x prime equals 0 has to correspond to x equals vt. And so we get 0 is a times x, which is vt, plus b times t. And we can take out t as a common factor. And so what we end up with is b equals minus a times v. So that's one relationship. So now we have x prime is a times x minus vt. The second clue is that light has the same speed c in both directions. So it travels a distance x in time t and travels a distance x prime in time t prime. If we put these two relationships in the two yellow equations, we get this relationship here. And we can cancel t from both sides, which gives us a simpler relationship as follows. Now, the same must hold for light moving to the left. So if we replace c by minus c in this equation, the white equation, that must also hold. So going back to the equation where we haven't cancelled yet the t, we get this equation. And then we can cancel the t and we get this equation here. So both of these hold simultaneously. Now what we can do is we can add them and subtract them to find values of c and d as minus a times v over c squared for c and d equals a. So putting those values now into our equations, we get these linear relationships here. The only thing left for us to determine now is the value of A. So let's call this transformation from xt to x prime t prime. Let's call it tv. It depends on the velocity v, so I'm going to call it t subscript v. Now the inverse transformation, which I'm writing as tv minus 1, would take us from x prime t prime back to xt. Now what should this look like? Here is where we require a third principle, and it is related to symmetry in that no inertial frame is special. And we call this the principle of relativity. So what does it say precisely in this case? Well, it tells us that x prime has to be equal to a times x minus vt, with Bob moving to the right at a speed v. And for Bob, x is equal to a times x prime plus v times t, with Alice moving with speed minus v. So this tells us that the inverse transformation has to be the same transformation, but with v replaced by minus v. So let's start with x equals a times x prime plus v times t prime. And let's use these two relationships that we have for x prime and t prime. And after some algebra, which I'll leave you to work out for yourselves, it's not difficult, we get this expression here, which leads to this expression, which is an equation for A. And we can solve that easily to get this value of A, 1 over some factor 1 minus v squared over c squared square rooted. By convention, we call this factor A gamma. So we end up at the Lorentz equations, or the Lorentz transformation from xt to xt prime, where this factor gamma is greater than 1, because the velocity always has to be less than the speed of light. And so what are the consequences of this? Well, we've already seen time dilation, and we derived that from different considerations, a more fundamental consideration. We can now also extract other effects such as length contraction. So let's first start with time dilation. And let's say we have two events. In Alice's frame, these occur at a separation of delta x, and the time between them is delta t. So what is delta t prime? Well, let's say from Bob's point of view, they occur at the same location. So delta x prime is equal to 0. Now, if that's true, the first of these equations becomes 0 is gamma times delta x minus v delta t, which leads to delta x is v delta t. Now we can substitute this into the second of these equations, the yellow one, and we get this expression here. Now, using the definition of gamma, we can write this equation as delta t prime is delta t over gamma. Or alternatively, delta t is gamma times delta t prime. And gamma, as we know, is always greater than 1. And so the time between these two events in Bob's frame is smaller than the time between those same two events in Alice's frame. Now let's look at a different phenomenon. We can write the equations with x prime, t prime replaced by delta x prime, delta t prime, and the same with delta x and delta t. And let's say that we've measured the length of something in Alice's frame. So we have to measure both ends at the same time, delta t equals 0. The first equation becomes delta x prime is gamma times delta x. Now let's call the length in Bob's frame delta x prime. Let's call that L0. And let's call the length in Alice's frame delta x. Let's call that L. And so what we end up with is L0 is gamma times delta L. And so what does this tell us? Well, this tells us, or L is L0 over gamma L, this tells us the length in Bob's frame is longer than the length in Alice's frame. So if we call L0 the proper length, that's the length that Bob sees while he's sitting in the train, then the length that Alice sees is shorter than that length. the moving length is shorter, because that's the length that Alice sees. And so we end up with this very odd conclusion, odd sounding, weird conclusion, which we call length contraction. Now, the final result is what we refer to as simultaneity. So let's go back to the equations that I wrote down for the last special case. Two events are simultaneous for Alice if obviously delta t equals 0. And so that leads to delta t prime is minus gamma v delta x over c squared. The delta t drops off. If delta x is not 0, then delta t prime is not 0. So simultaneous for Alice does not mean simultaneous for Bob. So we can see that one transformation, the Lorentz transformation, leads to three separate effects: time dilation, length contraction, and simultaneity. So it's a pretty remarkable set of equations.